Okay, here we talk about the induction and energy transfer. So a rectangular loop of wire of width L has one end in a uniform external magnetic field that is directly perpendicular to the plane of the loop. So you can see here, in this greater dot region, we have a magnetic field. The green arrow pointing into the page. And here we have a loop. We have a loop here, and then this hand holding this loop. So this field may be produced by a large electromagnet. The dashed line in the figure shows the assumed limit to the magnetic field, and the fringe of the field at its edges is negated. You are to pull this loop to the right. Pull this loop to the right. So there's a constant velocity pointing to the right side. And constant velocity. So it says there will be a flux change. The flux change because the magnetic field only appear in this region. So at the very beginning, if it is here, then the magnetic flux is the B times this area. If sometimes later the loop maybe move to this position, then the area is only this part. So the magnetic flux is actually changing. And just now we mentioned that if the magnetic flux through a loop is changing, then there will be induced EMF. Okay, so therefore a magnetic field and a conductor loop are in relative motion at speed v. The flux and the field through the loop is changing with time. Here, the flux is changing as the area of the loop still in the magnetic field is changing. So wait to pull the loop at constant velocity v, we must apply a constant force F to the loop, because you should pull this one out of this magnetic field region. Then you need to take a force to use a force to pull this out. So because the magnetic force of the equal magnitude but opposite direction acts on the loop to opposite you, the rates at which you do work, that is the power, is then P equals Fv. Actually, there will be a force acting on this wire, according to the Lorentz force, IL dl cos d. So you can see, to find the current, we first apply the Faraday's law when x is the length of the loop. X is the length of the loop, and still in the magnetic field. So this part is x. This part is x. So the area of the loop still in the field is L times x. L is the height. So L times x is this area. So L times x. Phi b will be b times a. A is Lx. So b Lx is phi b. So as x decreases, the flux decreases. Faraday's law tells us that with this flux, phi b decrease and EMF is induced in the loop, we can write the magnitude of the EMF as E. If you only take the magnitude, which means we may say we just take the absolute value here. So it is d phi b dt, d phi b dt. Take the absolute value. So BLX, and then take the derivative with respect to time. So BL is constant to t. X is changing because there's a velocity v here. So we have a BL putting outside, and then dx dt. Dx dt is nothing but the velocity or the speed. So dxdt is v. So in which we have replaced dxdt with v with the speed at which the loop moves. So far we know that EMF is BLV, and the current EMF and the loop is nothing but I equals E over R, E divided by R, which is nothing but the Ohm's law. So E is BLV, so I equals BLV over R. And actually, the three segments of the loop are marked with F1, F2, F3. Actually, if you move the current line, move the loop like this, there will be a force pointing to this side, because we have the I pointing upward here. The I pointing upward here. Let's see why the I is going in this direction. Because if you pull this loop to the right side, the magnetic flux pointing into the page is decreasing. So B induced is pointing out of the page. Sorry, it's decreasing. So it should point into the page. Yeah. So B is decreasing. So B induced is pointing into the page. And in this case, the loop current should be clockwise. So for this one, I is pointing outward. So if you still remember the Lorentz force, F equals I QVB D QV cross B L cross B. Yeah, something like this. So DL is pointing outward. B is pointing into the page. So I pointing outward. So DL also pointing outward. And IL cross B. B is pointing into the page. So you use your right hand rule. DL cross B. Then the F will pointing to the left side. So F1 pointing to the left side due to this one is the Lorentz force. Lorentz force. And for these two, F2 and F3 will cancel each other. So actually, it will use when you try to pull out this loop, it will something like F1 is counteracting you. You need to use some force, or you need to do some work to pull this loop out. So here it says, so for the using the Lorentz force, F1 is ILB sine 90 degree, ILB sine 90 degree. So F is ILB. And just now we mentioned that this one is I. This one is I. So yeah, so ILB, we plug in this value here. So we have B square L square times V over R. So this is F, and because B, L, R are constant and speed V, at which you move the loop is constant if the magnitude of the force applied is also constant. So this is constant if V is constant, because this one, and this one doesn't change. And finally, we find that the rate at which you work on the loop, you pull it from the magnetic field is P equals FV. P equals FV. P equals FV. If you still remember, W is integration of F dot ds. F dot ds. So actually, P is P. P is nothing but dw dt. dw dt. So it is somehow like integration of F dot ds dt. So ds dt is dv dt. So if it is a constant, it is nothing but f times v. So we have f times v. So we have the whole term square in the denominator and r in the numerator, or whole term square in the numerator and r in the denominator. So the work that you do in pulling the loop through the magnetic field appear in the thermal energy in the loop. So yeah, so it means you try to pull this one out, and then there will be current consumed by the resistance of this loop, and it becomes heat. So you do some work, this work becomes heat. So next, we consider something called the eddy current, 涡电流. For the previous page, we actually pull out a loop here, so the current can have a predefined path to go. Actually, if you try to pull out a solid conducting plate, so this is something like a cutting board, but a metal cutting board. Yeah, so a conducting plate out of a magnetic field, the eddy current are induced in the plate. A typical loop of eddy current is shown here. So it is similar. But yeah, here we have the dotted region with the magnetic field pointing into the page. And then this is the conducting rod. And if you try to pull this thing out, then the magnetic flux going through this dot is changing, is decreasing. So there will be eddy current. Even though there is no explicit path for the current to go, then there will be still some called eddy current going in this dot. So here we talk about the general form for the Faraday's law. For the Faraday's law, just now we only mentioned that E equals negative n times d phi b dt, and more generally, or sometimes we ignore the n, something like this here. So on the right side, we still have this term, but on the left side, we make it a line integral. So in chapter 29, if you still remember the Ampere's law, it is like integration, a closed integration of b dot ds equals mu naught I enclosed, like this. So here we change b to e here, and then but the right side is not something like that anymore. It is a derivative of the magnetic flux. So we can write, using the induced electric field, we can write the Faraday's law in its most general form as this one. Actually, this is, for this one, for the term on the left side, you have seen something similar in chapter 24. In chapter 24, we have learned something like V equals negative integration of E dot ds in chapter 24, when we talk about the electric potential. So at that time, we don't have anything dynamic. We only have charge like that. We only have current. At that time, I told you that if you go for a loop, then V should be always 0. But here, the case is different. We have some magnetic flux to be changing. Then after going through a loop, this EMF is not 0 anymore. It's not 0 anymore, which means that if you have a loop here and then you try to change the magnetic flux going through this loop, then there will be a current going through it. So it is like you try to go upstairs, and then go after a loop, then you go back to here, and then you keep going upward, and then but later on you still find you are still here, which is not practically true in our life, but actually this is something like that. This close integration, if you try to go for the E dot ds from here to here, because if you try to calculate this line integration in a mathematical way, which means that you pick a point, we have E, and then time dotted with ds, and then for the next point, E dot ds, so on and so forth for the whole loop, and then you add together. If there is no changing magnetic field, then after going through a loop, then it should be 0, because at that time it told you that when a point going to a path going back to the equal potential surface, then the voltage difference or the potential difference should be 0. But here is not the case. If you're going for the whole loop, when this magnetic flux is changing, then this value is not 0. It is actually this minus d phi b dt. So the electric potential, induced electric field are produced not by static charges, but by a changing magnetic flux. Therefore, electric potential has meaning only for electric field that are produced by static charges. It has no meaning for electric field that are produced by induction. So try to avoid using the concept of electric potential here. Otherwise, or at least you need to be very careful to use the concept of electric potential here. Otherwise, you get some wrong conclusion here. Okay, so here it talks about the Faraday's law. So here is a copper ring, and if the magnetic flux or the magnetic field is increasing into the page, so the B induced will be pointing out of the page, and in that case, using the right hand rule, your thumb pointing out of the page, your forefinger will be pointing to the direction of counterclockwise, like this, which means that E is pointing to the right side. For this point, pointing to the upward. At this point, pointing to the left side. At this point, and so on. Yeah. And it also tells you that for the path one, path two, here, equal EMFs are induced around path 1 and path 2, which lie entirely within the region of changing magnetic field, because we assume the magnetic field is uniform for this region, and then it changes in a static rate. So this d phi b dt would be the same for path 1 and path 2. And in that case, E dot ds will be the same for path 1 and path 2. For path 3, part of the loop is out of this region, so the d phi b dt is smaller for this case. So it says a smaller EMF is induced around path 3, which only partially lies in the region. And for path 4, there is no magnetic flux going through this one. So there's no magnetic flux changing. So no net EMF is induced around path 4, which lies entirely out of the magnetic field. So it also mentioned that the path is not a physical conductor, but an imaginary line. The changing magnetic field induced blah, 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 yeah. So let's see a sample problem here. So in the figure, takes R, capital R, and then d phi dB dt like this. So find the expression for the magnitude E, magnitude E of the induced E field at a point within the magnetic field at radius small r from the center to the magnetic field. Evaluate the expression for R equals this value. Okay, so here we have a closed integration of E dot ds. This is actually a line integral, closed line integral. So here we also assume that E is parallel to the ds. Because for ds here like this, ds here like that. So this inner product is nothing but a multiplication, EDS. And E, we assume E will be uniform over this circle, over this path. So it is nothing but E times closed integration of ds. So this is the circumference of the circle, which is 2 pi r. 2 pi r. Okay, so next, phi b. Phi b is b times a, because b is uniform over this region. So we don't need the integration. And b times a is the area of the circle, which is pi r squared. Okay, so next we need to take the derivative of phi b with respect to time. So we have pi r squared, which is a constant, and then we have the dB dt. So dB dt, we take this value, so it will be 0.13 pi r squared. So according to the Faraday's law, we have an integration of E dot ds equals negative d phi b dt. Okay, so we have E times 2 pi r equals 0.13 pi r squared negative. So we have E equals negative 0.13 over 2 r, because pi and pi will be cancelled, r and this r will be cancelled. Which means E, the magnitude of E should be 0.13 over 2 R volt per meter. And if we evaluate E at R equals 5.2 centimeter, it will be 0.13 over 2 times 0.052, which is 3.4 millivolt per meter. So this is for part A, and for part B. We need to find the magnitude E outside the outside this region. Outside this region. So in this case, d phi b dt is different. D phi b dt is nothing but this region. So which is 0.13 pi capital R square rather than small r square, because this impedance loop, something like that, is something outside. So the magnetic flux only consider the inner part and all the way this part. So for Faraday's law, we have E dot ds integration equals negative d phi b dt. So similarly, E dot ds is E times 2 pi small r, 2 pi small r. We still need to consider this r for this path. And then it is negative 0.13 pi capital R square. So we have a absolute value of E should be 0.13 over 2. And then pi and pi can be cancelled. R cannot cancel anymore because one is small r, one is capital R. So it will be R, capital R square over small r. Okay, so now if we try to evaluate E at R equals 12.5 centimeter, it will be 0.13 over 2 times R, capital R is 0.085 quantity square over 0.125. So this is nothing but 3.8 millivolt per meter, which is slightly larger. Okay. So here we'll talk about the inductor and inductance. So an inductor is a device that can be used to produce a known magnetic field in a specified region. If a current I is established through each of the n windings of an inductor, a magnetic flux phi b links those windings. The inductance L of the inductor is L. So this is the definition of the inductor. The definition of the inductor. Something like the definition of the capacitance is Q equals CV. This is the definition of the capacitor. The definition of the inductor is this one. This one is like the magnetic flux divided by the current. This is the C will be Q over V, the charge divided by the voltage difference. Here is the magnetic flux divided by the current, which means the voltage will generate the charge. Here, the current will generate the magnetic field, and so as the magnetic flux. So if you increase the current, then the magnetic flux will increase proportionally. So this constant is called the inductance. So the SI unit for the inductance is Henry, H. So 1 Henry is this one. And this crude inductor with which Michael Faraday discovered the law of induction. So this one, in the Royal Institution. So in those days, amenities such as insulated wire were not commercially available. Isolated wire, because you can only find a wire, but if you try to make it into a solenoid, then they will touch each other, which is not what we want. So Faraday really need to use some insulated wire, which means there are some insulator bounding the wire. So it's that Faraday insulated his wire by wrapping them with the strip cut from one of his wife's petticoats. Yeah, he used one of his wife's petticoats and then cutting it into strips and then try to wrapping the wire. So consider a long solenoid of the cross section, no area A. The first linkage there is this one. So N is the number of turn. N is the number of turn. Small n is the number of turn per unit length. So L is the length of the inductor. And then phi B is B times A. Nothing special. And if you still remember, the magnetic field generated by the solenoid is mu naught times I times N. So we can plug in all the things there. So L equals N phi B over I is the definition of the inductor. And then N phi B is this one. So we plug this one here. And also we know the magnetic field generated by this solenoid is this one. So we plug this one into here. So we have NL mu naught INA over I. And we slightly rearrange the term and we move this small l into the left side. So which means this is the inductance per unit length. Inductance per unit length equals mu naught. I and I are cancelled. I and I are cancelled. And then we have n squared here. L already moved to the left side. We have A here. So we have mu naught n squared A. So which means that the inductance per unit length, mu A is a constant. If we want to have a larger inductor, then the area should increase, or the number of turns per unit length should also increase. Otherwise, you should have a longer inductor. Actually, even though you are not ECE student, you may think, oh, why we need to know inductor. Actually, the antenna on your smartphone or on your iPad or on your electrical device, the antenna is actually a inductor. Although it is not something like a wire doing like that, but actually, a few years ago, a few years ago, the smartphone, you can still disassemble it. Usually, it has a cover. You can still open it, and then you can change your battery, something like that. Actually, there will be some coil on the cover side, and it is actually some antenna for different applications, something for Wi-Fi, for 3G, 4G, for GPS. There will be different antenna for different purposes. Okay, here we talk about the self-induction. Self-induction. It says if two coils, which we can now call inductors. So this is the electrical symbol for the inductor. So we have something like this, like this, like this. So we have a multiple coil. So which we can now call inductor and are near each other. The current I in one coil produce magnetic flux phi B through the second coil. So let's see this setup. We have a battery here. We have a tunable resistor here. So if you try to move this tip to the left or to the right, then this resistance may vary. If you move to this part, the resistance is larger. If you move to this part, the resistance is smaller. It only tells you that this one is a symbol for a tunable resistor. And just ignore this part, then there will be a current going this way. The current will be going this way. Okay, so as much as there is current going through this inductor, and of course there will be magnetic flux. There will be magnetic field generated by this solenoid or the inductor. So we have seen that if we change this flux by changing the current, an induced EMF appear in the second coil according to the Faraday's law, which means if you have a coil, the current going like this, so the first coil will generate a magnetic field pointing downward. Using the right hand rule, you can determine this. You can use your forefinger, follow this direction, and then your thumb will be pointing downward. So the first round, the first coil will generate a B field pointing downward. And if it is changing, it will generate a changing magnetic flux for the other coil, for example, the second coil, the third coil, and so on. If this coil is changing, if this magnetic flux is changing, then according to Faraday's law, it will generate the induced EMF. If it is increasing, then the B induced will be pointing upward. If it is increased, the B induced pointing to the other side. And there will be a induced current pointing to the opposite side, which is something like a voltage drop, Okay, so so an induced EMF in the first coil as well. So this process is called self-induction, 自感应, and the EMF that appear is called a self-induced EMF. It obeys the Faraday's law of the induction, just as other induced EMF do. So thus, in any inductor, such as a coil, a solenoid, or a toroid, a self-induced EMF appears whenever the current changes with time. The magnitude of the current has no influence on the magnitude of the induced EMF. Only the rate of change of the current counts. Yeah. So. Okay. So So it follows this one is the definition of the inductor. Just now it is L equals N phi B over I. So you move this one to here. So we have Li equals N phi B like this. And here we use the Faraday's law. So we have d phi b dt. So we have Li here. So we have Li here. So it becomes El equals negative dLi dt. And L is a constant to time. So we move this one out. So this is the physics point of view. Most of you are easy to learn, so you should have learned the circuit analysis. And at that time, usually we will write it as VL equals L d I dt. Yeah, I usually use this one. I seldom use this one, although the textbook is written like that. And of course, for the capacitors, we have I equals CdV dt. Yeah, something like this. For capacitor, I equals CdV dt. For the inductor, we have V equals L di dt. Yeah. Although we will not teach chapter 27 and chapter 31 in this semester, but yeah. But I suppose you should know that. And induced EMF EL appear in any coil in which the current is changing. So if the current is changing, then there will be voltage drop there. Then there will be voltage drop there. Which means if it is just a constant voltage, then there will be no voltage drop. And there will be no voltage drop. Yes, most of you should have learned the circuit analysis. So for the phasor for the inductor, it should be like J omega L. So when omega equals 0, which means it is a DC, then this one will be 0. CL omega equals 0 will be 0. Then there will be no voltage drop. But if omega is large, which means the current is changing rapidly, then the induced EMF will be stronger. Yeah. Okay, so this is something like the RL circuit. If a constant EMF is introduced in a single loop circuit containing a resistance R and inductance L, the current rises to an equilibrium value E equals R according to this one. So this is quite simple. Yeah, so we have a circuit like this. Let's see. So we have a circuit like this. Yeah, so we can write the KVL for this one. So we have E equals R times I plus L di dt. L di dt. So this is nothing but a first order constant coefficient ODE. And we can solve it by, let me try to write it like this, L di dt plus Ri equals E is a constant. So let us divide L on both sides. So we have di dt plus R over L times I equals E over L. And then we can just change this one to S plus R over L. And then this is the original function. We change it to 1 equals 0. So S equals negative R over L. So we have I equals A times exponential to minus R over LT, something like that. This is the complementary solution. And then for the particular solution, particular solution, since this one is a constant, so IP is another constant, we plug in here. So we have a E equals R times B plus L times di dt. The derivative of a constant is a 0. So B is E over R. So I equals IC plus IP, which is E over R. And then also we will assume that E over R minus A exponential to minus R over LT. Yeah. And we assume that I0 is 0. So we have E over R minus A, because when we plug in T equals 0, this is 1. So we have A equals E over R. So finally, we have I equals E over R 1 minus exponential to minus R over LT, something like this. Or actually, most of you are learning signal and system. So you can actually take the Fourier transform of this equation. You will get this one is I j omega plus R over L. Take the derivative. We will have j omega here, and then we will have I j omega like this. And then the other side will be E over L, which is nothing but a constant. So I j omega will be something like E over L, and then j omega plus R over L, something like this. So this is the first order response. Yeah, well, of course, this is something out of scope of this course. So actually, we derived this one just now, and then tau L is called the inductive time constant L over R. Yeah. So when the source of a constant EMF is removed and replaced by a conductor, the current decay from So you can also derive this one similarly. Okay, so let me stop here and